all, in this video, let us discuss about ResNet architecture. So it was a 2015, it was a major breakthrough. There was a residual network which is called as ResNet, and they were the winners of 2015 ImageNet competition, and they have got error rate very less. They have achieved the first place in 5 main tracks of the ImageNet. Other than this classification challenge, they also had a lot of other challenges like ImageNet classification, and then ImageNet detection, and then ImageNet localization, and then COCO detection and COCO segmentation. And then this network, residual network, won all this competition. They were able to train networks which were 152 layer deep, and this network is called ResNet 152. People still use this a lot as their backbone network. Say, for example, like nowadays we are using mask CNN, right? So people are using these as the backbone of the network and the ResNet network. And now the question that we should ask ourselves is that, like, why are they able to train all these deep networks, right? So let us discuss about that in detail. Basically, like we have already have a good knowledge on all the way from 2010, 11, 12, 13, 14, and 15. And we have seen several networks, right? And there were certain deaths and the errors were high. And this was the pre-deep learning error. So they were able to achieve around 25%, right? So like slowly the error rate was reduced, right? When like actually we have seen several networks, right? So actually it started, we have started with the discussion on AlexNet, right? AlexNet from 26%, it got reduced to 15%. And then ZFNet from 15%, it is reduced to 11.2%. And then VGGNet, it is reduced from 11.2% to 7.2%. And in GoogleNet from 7.2%, it is reduced to 6.7%. And actually in ResNet, it is reduced from 6.7% to 3.57%, right? So this is 2015 ImageNet winner with a error rate 3.57%. So the first truly deep network with a 152 weight layers, right? So this is the one which have really got less error. Actually, we can say that the top error rate is less, and it is 3.57%. And then we can look over here. Let us discuss about these now. So here you can see that they have plotted the training error loss, right? And they have plotted the loss, the decrease of loss with respect to the different iterations. So you can see over iterations here, the error rate is marked for several iterations, right? And so here we can see a plot where they have plotted the error percentage on the y-axis, and you can see iterations on the x-axis. So here you can see plain networks, and here you can see that ResNet, right? So here you can see that plain 18, plain 34, and ResNet 18 and ResNet 34. So what they did was, like, they were doing some experiments on the CFOT and data set. So like they have used the images of size 32 cross 32 with the 3 channels. And then this data set, what they tried was, they tried increasing the number of layers in the network. And like this is the training data set, right? So if they have a deep network, which means they have a lot of non-linearities and parameters, and it should be able to at least overfit on the training set. So actually, what happened was, like, as they increase the layers from 20 to 56, this is the test set and this is the error on the training set. So you can see both on this data, right? I mean, on this plot, right? So you can see that the thin curve denote the training error and the bold curves denote the validation error of the center crops. And in the left, you can see plain networks of 18 and 34 layers. And here you can see ResNets of 18 and 34 layers. So in this plot, the residual networks have no extra parameter compared to their plain counterparts. So actually, when it was tried like with the 56 layers, it was giving a very good performance, but the problem is with the vanishing gradient. It is very difficult to train very deep networks, right? So like we are going to study all these things in detail. When we do residual networks, like how the residual modules will work, we will try to understand that. Using residual models, we see that deeper the network, the lower the error, right? So deeper the network, the lower the error. So that is the concept behind this network. So on the training data set, the error is almost the zero. It classifies every instance correctly. It is almost like overfit on the training set. As expected, the 20-layer deep network has more error than the previous one, right? So also in the test set, 110-layered network, lower error, and 20-layer network, this is the, because they were using residual networks, the deeper networks are also able to generalize. This is what the understanding for the residual network. So here we can also notice the plot over here, like you can see both the curves over the blue curve and the red curves, and this is giving, see, like from this itself you can identify that what is that blue and red basically tells us. And also like so this is very clear to us, like which is saying that which stands for the training error and which stands for the validation error, right? So you can see like some error percentage drop over here. So the most interesting using residual networks, we will be able to use deep networks. So this is the understanding about this residual networks. So this is the revolution of the depth. And if AlexNet works this way, like VGGTNet, and like a little double the size than that, but the ResNet, no, it is actually many times the size of VGG19 when we have 152 layers. Right, because like a VGGNet was 16 layers deep, but when we compare this ResNet, this is 152 weight layers, right? So however, at runtime, it is faster than VGGNet, even with the 8 times more layers. So this is the most important point we have to remember. Even if you train it on single GPU, we don't even know 2 to 3 weeks. It is very much feasible. And we will be comfortable with this residual networks, right? So we don't have to wait for weeks, like it executes fast, right? So we will try to understand what ResNet is. Basically, like so now look at this residual network. Now look at this residual networks over here. So here we have visualization for 34 layer, and like you can see like VGGNet, 34 layer plain, 34 layer residual, and this is very popular, right? So this is a very popular network basically. And here we simply have visualization of a 34 layer deep network where we have lot of convolution layers of size 3 cross 3, right? Now let us try to understand this 34 layer residual network, what we have is like there are some connections, right? So these connections are called as residual connections or skip connections. So after pooling, the size is 56 cross 56, and there is no pooling over here, right? So the spatial dimension will always remain as 56 cross 56 with one padding. So what we are doing here is that we just used a convolution layer, but the output of the convolution layer, we are also adding inputs. So you can see over here, from here, right? So in each and every place, you can see a pooling over here, right? So there are skip connections, sorry. There are skip connections actually, right? So from here to here, right? So here there is the image and here there is the output, right? So there is change in the spatial dimension and we can have skip connections. So we have 1 cross 1 convolution layer and you have 3 cross 3 convolution layers, right? And you can see that, right? So you can see lots of 3 cross 3 convolution layers over here, and 64 to 128 you can see, then 128 to 256 and 256 512, right? So this is clear, right? So the feature map will be increasing, right? So layer by layer, you should try to understand over here. So how this actually looks like, this is how it looks like. There will be a weight layer, and then here there is a weight layer and a ReLU is used, and there is another weight layer which is called as ReLU, right? And then here what is happening, after 2 ReLU layers, we have this output is function of X plus this X. Right? So let us try to understand this in detail, what the residual network is. So we have 64 dimension input, say feature map is 64 feature maps. So like we then do 3 cross 3 convolution. So here we can do 3 cross 3 convolution, and then the size does not change. And then here we can do another 64 cross 64 3 cross 3 convolution, and the output of this is the addition of the output that you get from here plus this X. So is that clear? So this is going to be this f of X and plus this X. So which is nothing but the identity, right? So function of X plus identity. So like after addition also we perform another ReLU over here. So what is happening here? Now the output function will be f of X plus X, right? So the identity is X. What is the advantage of doing this, right? So one argument is that it learns identity functions better. What does that mean? Like it means, suppose we have X, and after this layers, and after this f of X is also equal to X. F of X is also equal to X. Then also this weight matrix has to learn it, right? So here we may need another identity matrix over here, and we need another identity matrix over here, right? So if we have, if we are able to learn these identity matrix, we will be able to achieve this. So what do we think about identity matrix is easy? Like actually we have initialized these weights something like 0. So if we are doing what kind of initialization, whatever you do, like weight initialization, like random numbers close to 0 distributed randomly, and they will anyways they are going to start from a value close to 0. So the 0 matrix varies, right? So this is not actually very easy task, but here that is the reason it is added with the function of X with the identity matrix. So we start with the same initialization of weights. Say here if it is close to 0, here if it is close to 0, and if the output is 0, since we are adding the identity matrix, right? So here if this is going to be 0, but at least it can learn from this identity matrix, right? So the other argument is that like easier to understand, like it provides the gradient superhighway. So the gradient from here in our plane network, so let me take that diagram so that you can understand that in a better way. So here, this is what the skip connection is happening over here, right? So like this is how the path is taken, right? A part of the gradients will come all the way. So like here we can see that it comes to the starting position, right? So it mitigates the problem of vanishing gradient, which solves the major problem with this ResNet, because the AlexNet and some other networks were suffering with that vanishing gradient problem. And those problems are really solved by ResNet, right? All the way from the input, like where the connection starts. So this is what I was telling, right? So this we can consider as an ensemble of different layer sizes. Yes, so that is clear, right? So this is looking something similar to ensemble, right? So like this is what it is going from one to the another one and to the another one. So in that case, we can call it as ensemble network, right? So finally, we get the output and the see the part by part, it is actually part by part, it is actually working, right? So you can see the various skip functions, and you can also try to understand here like why some lines are given as dotted lines. And there are several arguments like ResNet is ensemble of networks of different depths, and it is also more powerful, right? So there are more comments about this network, about batch normalization after every convolution layer, and it also uses Xavier to initialization from Hethel, and it also uses stochastic gradient descent with the momentum 0.9, and and also it uses learning rate 0.1 divided by 10, and also it uses mini batch size of 256, and then it uses a weight decay of 1 e power minus 5, and there are no dropouts over here, right? So what we have seen is like the ResNet is being the first place in all the 5 main tracks, like ImageNet classification, ImageNet detection, ImageNet localization, COCO detection, and COCO segmentation. And we have seen like how this part is being done, and how this 34 layer residual network is different from VGG 19 and 34 layer plane. And you can see the identity block over here. There you can see like convolution 2D batch normalization ReLU, and then convolution 2D batch normalization ReLU, convolution 2D batch normalization. Then finally also there is ReLU is done, right? So this is what we have seen. So in the convolution block, what you can see is like here, what is the added one? Here you can see that convolution 2D batch normalization, right? So we have a very good idea on what is this convolution 2D, and we also have come across this batch normalization, right? So the next one is about after this the story was little boring, and in 2016 the winners were CU Image team, and here the landscape becomes saturated, and their error rate reduced to 2.99%, and this still decreased, and they were the winners of 2016, and it is the best model seems to be ensemble. And there are various networks, and but it is nothing nothing interesting. Actually, it is not an interesting thing to cover, so it is not really required to learn about it. So the next one is about squeeze and excitation model, which is nothing but CNET 2017. And here squeeze and excitation block that can be added to a convolution layer, squeeze and excitation networks. So that is basically called a CNET, and that could be added to any conv layer. And what they do is they add parameters to each channel of the convolution block so that the network will adaptively adjust the weight of the network. So they claim that the feature maps, say for example, you have 64, some are more important than the other. They learn weights with which they can either increase the value of what the network thinks is more important feature map and decrease the value or increase the value. So that is how the decision is being taken. So what they do is, say for example, you have as the volume height, width, and height and width, and then squeeze operation, right? In the squeeze operation, they bring down the feature maps through spatial dimensions through 1 cross 1 convolution. And once you have C2, which is less than C1, and then it learns to C2 weights, one for each channel C2, and they learn C2 weights, and then again it gets multiplied with the C2 feature maps to the final output, right? So this is the squeeze part and this is the excitation part, C1 to C2, and then they learn these C2 weights, and then using these weights, each of these will use the first one and then multiply each channel of this C2 volume with this feature map, right? So this is what happens. This happens to be a large number. The network must have realized that this is a very important feature map. And similarly, for the large feature map, maybe this number is very low, and it could be sometimes unimportant feature also, right? So they got an error rate of 2.251% top error on the test set, and actually 25% improvement on the winning entry of 2016. And winning entry comprised a small ensemble of CNETs that employed a standard multi-scale and multi-crop fusion strategy. And one of the high-performing networks constructed integrating AC blocks with a modified ResNet, right? So that is why we are studying this with this ResNet, right? So let us try to understand this little more better. In squeeze, shrinking feature maps through spatial dimensions and then global distribution of channel-wise responses. So in excitation, what happens is it learns weight to explicitly model channel association. So getting mechanism to produce channel-wise weights. So then it reweights the feature maps, right? It reweights the feature maps. So the performance is actually saturated. That is what being from 16 and it has come to 3. Again, it comes down to 2.251%. Now they are creating some web skill competition, but the ImageNet satisfaction, ImageNet competition is no longer existing now. So why do we use ConvNet? So that also we have to try to understand why do we use convolution network, because the error rate what we have seen is like actually the error rate has reduced a lot, and comparatively to the traditional model. So the other models error rate we have seen till now, like how the error rate was decreasing and in what way actually this ResNet and the CU image or SENet has taken the next steps to win this competition. So like what we could figure out is like from ResNet to SENet, squeeze and excitation network, like we could see the error rate is being saturated. So that is the reason it was not again continued further. right? So hope this session is clear to you. Like we have seen how the residual network basically works, right? So that is what we tried to understand. And I hope this is clear to you. So let's meet in the next session.